If we look at the surface fluxes and the SST tendency, obviously you will need to invoke some ocean dynamics to explain it. The book calls it a paradox, but I'm not so sure that's necessarily a paradox. So this is the long-term average components of the surface heat balance for the North Indian Ocean, which is not always clearly defined, but generally it's up north of 20 south. All the way to the northern border, and north of the equator, obviously north of the equator, from the equator to 10 north and north of 10 north. The idea is to just look at the SST tendencies and what is observed. So this is computed by using a simple balance where you assume that the net flux coming in is distributed over some depth like 50 meters, and then depends on the density and the specific heat, of course, and look at the entire Indian Ocean, DJF, MAM, JJA, SON, and the annual mean. So you look at solar, long wave, latent heat, and sensible heat, and the net flux. We will see in a minute these variations. Obviously during winter monsoon you have dry cold air. In the MAM you have weak winds, clouds not there, and during SON you have winds in the intermonsoon being weak in the north, but the southeasterly trades are strong, and so on. So you can see some substantial seasonal variability in the shortwave radiation coming in. The long wave tends to be smaller but has much less of a seasonal variability. Latent heat flux you would expect to have a larger variability balancing the surface heat flux, and sensible is always low on the ocean typically. Okay. So there is the net heat flux. Even in DJF for the entire Indian Ocean north of 20 south, there is a net heat flux which is smaller, but MAM it's much larger. Even during JJA there is. So throughout the year there is incoming net surface heat flux at the interface of the ocean and the atmosphere, which if it was trapped in the 50 meters you would expect a warming of several degrees per month. But obviously the observed tendencies of SST are not that large at all, and in fact there is a cooling during JJA, which is obviously dominated by the Arabian Sea, Somali upwelling and so on. The simple model will give you much different numbers, as you can expect. So that's what is called a paradox here, but essentially it just means that one-dimensional balance is not valid. You need some heat flux, heat transport in and out of this region. There is the Indonesian through flow, which we are not discussing much here, and there is the meridional overturning circulation that I mentioned. There are some theoretical details. For example, if the deep ocean is warmed, theory by Boccaletti and Philander and Fedorov would say that the upper thermocline adjusts, and there is some evidence that this actually does work. So when you have such a strong meridional stream overturning heat coming in from the Southern Ocean, seasonal variability of that is going to have obviously not only impacts on the heat balance but also on the thermocline adjustment. So those kinds of things are not included when we do that. But the main thing here is monsoon is considered an upper ocean interaction process, so we will not talk much about the overturning circulation, and we keep talking about heat content without explicitly saying in what depth. Okay, so you have to be careful about that as well. And there are these other numbers. North Indian Ocean, similar story, net heat flux throughout the year, north of 10 north as well. Net heat flux, but annual SST rates are not explained without having dynamics. So if you just look at the 850 hectopascal zonal wind component throughout the year, this is longitude, latitude section that is shown for seasonally. So in the southern hemisphere, south of 10 south, we have the southeasterly trades, which are steady with some northward migration with season during the southwesterlies. And then you have the northern Indian Ocean, which has westerly winds almost throughout the year, especially the equatorial region, which is very unusual compared to other oceans where the winds are predominantly easterly, right? So corresponding to that, you have heat fluxes into the North Indian Ocean. So you have heat losses here in the spring summer months, boreal spring summer months, that are pretty large, and you have heat gain during the early part of the year and fall months as well. So the net heat flux, as we saw already, is still positive, and there is heat loss here in the early part of the year and later part of the year, with heat gain throughout much of the year. So this is typical of the Indian Ocean, and the match with the sea surface temperature variability we saw being mostly warm throughout the year is consistent with those heat fluxes. But in general, when people do heat budgets, SST processes, we think about the surface mix layer, which we have talked about, made up of heat loss evaporation creating convective mixing and above the thermocline, and wind driven turbulence, which, as I mentioned, is proportional to the cube of the so-called friction velocity. Together they give the freshwater flux, the buoyancy flux or the heat flux, and the freshwater flux together, combined with the kinetic energy from the winds, to determine how much total energy is available for entraining colder, heavier waters from below the thermocline into the mixed layer. If the mixed layer wants to get deeper, then you need to entrain mass below and chew into the thermocline. Okay, so some are stabilizing influences, some are destabilizing influences, and wind is a mixing effect. So the net heat budget depends on all those things. We don't get into those kinds of details. Most of the results presented in the book, in the chapter, are from this intermediate ocean model of J. McCreary, which is a very cute toy model which can produce lots of very useful insights, as you can see from the nice papers by J. McCreary, his students and collaborators, and so on. It is the so-called 2.5 layer model. He has other versions where he increases the number of layers, but essentially, if you remember way back in an older chapter, we looked at the 1.5 layer model, which we will come back to later on, where we assumed that above the thermocline there is an active layer which has currents and temperatures and heat advection and so on, and then we assumed a deep motionless layer where pressure gradients go to zero and velocities are of course zero. Here it's split into two layers, H1 and H2, so some specific simplifications are needed to create these cross-interface fluxes and heat balance, momentum balance, and of course the equation of state and so on. The thing to remember is that this model is forced with winds, so if there is a biennial signal in the model, heat transport and so on, it's essentially coming from the fluxes at the surface, like winds and freshwater fluxes and heat fluxes. Okay, so this is not a coupled ocean atmosphere model. So the story is half in that sense, that the fluxes are being produced by prescribed surface forcing, so which means it doesn't explain where the time scales in the winds themselves come from and the surface fluxes themselves come from. Given those fluxes, the model is able to produce advective fluxes and transports within the ocean. That's something that has to be kept in mind, because a lot of the arguments in the book are based on this simple model forced with surface fluxes, and that's not completely made clear. So I just wanted to be sure that you are aware of that.